Good evening, dear students. Next, we can go through the nomenclature of this heterocyclic compounds. In our last session, we had discussed some of the heterocyclic compounds, isn't it? That we have seen furan, thiophene, pyrrole, then pyridine, etc. So many compounds we had seen. Now you have to go through the nomenclature of these heterocyclic compounds. That is, normally we will be dealing with the IUPAC nomenclature. IUPAC nomenclature of these compounds. Okay. So the first point to be noted down is that normally this oxygen, heteroatom oxygen, it is represented by oxa. Okay. Then for sulfur, it is represented by thia. That we have discussed in our last session, isn't it? Then for nitrogen, it is represented by ASA, A-Z-A. Then Sila for silicon. Sila for silicon. Then for phosphorus, it is phospha. For phosphorus, it is phospha. And for boron, it is bora. So this is how these heteroatoms are named. For oxygen, it is oxa. For sulfur, thia. Nitrogen, asa. Then for silicon, it is sila. Then for phosphorus, phospha. Then for boron, it is bora. And also, if two or more heteroatoms are there, then usually we will be representing it by the letters, by prefixing it with di, tri, tetra, etc. Isn't it? The normal words. If more than one heteroatoms are there, we will be representing it by this. Okay. Then again, there is a order of citation for this heteroatom. If more than one type of, order of citation. That is, if more than one heteroatom are there. For example, if two different heteroatoms are there, say for example, then oxygen and sulfur, or oxygen or oxygen and nitrogen. In such cases, if two heteroatoms are present within the same compound, then how will you name these compounds? Okay. And also, there also an order is there for writing this. Okay. For representing this type of compounds, since it is having two different heteroatoms, isn't it? Here, one heteroatom is oxygen and the another one is sulfur. Here it is oxygen and the another one is nitrogen. Okay, so we have to follow one order. That is, if two heteroatoms are there, first of all you have to represent oxygen, or you have to name oxygen. Then you have to name sulfur, then nitrogen, then phosphorus, silicon, etc. Okay, so you have to name only in this order. So if a heterocyclic compound having oxygen and sulfur are there, you have to name first oxygen, then sulfur. And if it is oxygen and nitrogen, then first of all you have to represent oxygen, or you have to name oxygen and then nitrogen. Okay. And if oxygen and nitrogen are present in the same compound, we can represent it as, first it is oxygen. For oxygen, it is oxa, isn't it? Then for nitrogen, it is asa. So we can represent it as oxasa. Okay, for oxygen and nitrogen. So for sulfur and nitrogen, how will you represent? So for sulfur and nitrogen. So sulfur will be coming first, then comes nitrogen. For sulfur and nitrogen, we can represent it as sulfur, it is thia, and for nitrogen it is asa, so it is thiasa. Okay, so that is how we have to represent these heteroatoms. Then the next point is that 1, 2. Then the third point, suppose for a 5-membered ring, if it is a 5-membered ring, the name will be ending with, if it is a 5-membered ring, or the name will be ending with the letter OLE. Okay. And again, if it is a 6-membered ring, the name will be ending with INE. If it is a 6-membered ring, it will be INE. And for a 7-membered ring, it will be ending with EPINE, EPINE. And for an 8-membered ring, it will be ending with OCINE, OCINE. Okay, so for a 5-membered ring, OLE, 6-membered INE, 7-membered EPINE, 8-membered OCINE. Okay, so that is how the suffixes are represented. Suffixes are represented. Okay. Then again, one more point to be noted down is that in the case of a compound having a heteroatom, the numbering will be starting like that. The heteroatom will be getting the lowest number, or if suppose this is a nitrogen compound, or suppose this is pyrrole. Okay, so we have to number starting from this nitrogen, so that this nitrogen will be getting the least number. Okay, nitrogen will be having the least number. So nitrogen 1, then 2, then 3, 4, 5. So here what about the direction of this numbering? It is in the anti-clockwise direction. So the numbering will be in the anti-clockwise direction in the case of this heterocyclic compounds. Usually the numbering will be in the anti-clockwise direction, and also the heteroatom should get the least number. Here the heteroatom is having the least number. Then one exception is there, that is in the case of quinoline and isoquinoline. Quinoline, the structure, it is like this. Quinoline, both are a 6-membered ring, isn't it? This is quinoline, and again this is isoquinoline. Quinoline and isoquinoline. So here one nitrogen atom is there. At this position, one nitrogen. So this is quinoline, and here this is isoquinoline. Isoquinoline. So here, see, the numbering starts from this nitrogen, that is 1, 2, 3, 4, then 5, 6, 7, 8, then 9, 10. Okay, 9, 10. So this is how the numbering is going on. That is like this. That is in the anti-clockwise direction, and also the nitrogen should be having the least number. Okay. Then again in the case of isoquinoline, there is some difference is there. That is the numbering, it is from 1. That is from this position. So this position is 1. Then nitrogen will be having the second position. Then 3, 4, 5, 6, 7, 8, 9, 10. Okay. So this nitrogen here in the case of isoquinoline, nitrogen will be having numbering 2, or the position is at 2, and in the case of quinoline, nitrogen is at the first position. Okay, so this is an exceptional case. Then in the case of furan, so this is furan. So how will you number? Oxygen will be having 1, then 2, 3, 4 and 5. So here what are the alpha positions? That the alpha position means the position to which the functional group is attached, isn't it? Here this is the functional group. So 2 is the alpha position. Again, this position, this 5 position is also an alpha position, isn't it? Or it is an alpha dash position, since it is directly attached to a functional group. Then what about the beta positions? 3 and 4 will be the beta position. Beta dash. So here alpha positions will be 2 and 5, and the beta positions will be 3 and 4. So this is how numbering will be going on. So this is also in the anti-clockwise direction. Hope you are clear with this. The nomenclature of this heterocyclic compounds, this I told that just for your information only. Then the next is you have to go through some of the 5-membered heterocyclic compounds in detail, and also the general method of preparation for this 5-membered heterocyclic compounds. 5-membered heterocyclic compounds. Okay, the general method of preparation. General method of preparation, and this general method of preparation, it is very important. It is a very important synthesis, and it is called as Pal-Nor synthesis. Pal-Nor synthesis. This is very important. It is an usually asked question, Pal-Nor synthesis. So here in this synthesis, normally we are discussing this 5-membered heterocyclics. So here this general method of preparation will be dealing with these 3 compounds, that is the preparation of pyrrole, preparation of furan, and also the preparation of thiophene. Okay, so here we are discussing the synthesis of these 3 compounds, and also the starting compound, it is a dicarbonyl compound. Okay, it's a dicarbonyl compound, and also I will be drawing the structure of this dicarbonyl compound. CH2. Okay, then again C, R, then again Cr, R and R dash. Okay, so we can identify the two alkyl groups. Then again double bond O, here also double bond O. So here this is a keto form, isn't it? This is a dicarbonyl compound. That means it is having two CO groups. So we can name this compound as a 1,4-dicarbonyl compound. 1,4-dicarbonyl compound. So here this dicarbonyl compound, we can number this carbon as 1, this is 2, this is 3 and this is 4. So at the 1 and 4 positions we have got a CO group and it is a keto form of this compound. And again here there is a chance for tautomerization, isn't it? So keto, enol, tautomerism. So we will be obtaining the enol form. And how the enol form is obtained? See here, this CO group, the electron pair will be shifting towards this oxygen atom so that this oxygen will be getting a negative charge. Okay, then what happens is that this electron pair will be shifting towards this bond. And what happens to H plus? This hydrogen will be moved to this oxygen to form H. It will be, hydrogen will be losing an electron, isn't it? So it will be moving as H plus and it will be joining this O minus. Hope you are clear. See here, at this position, the double bond or the electron pair will be shifted towards this oxygen atom. And again, the rearrangement will be like this. This hydrogen will be moving as a proton and therefore this electron pair will be moving towards this position. So this carbon will be having a double bond, isn't it? So I will be representing the structure. Then the first one, RC. See here, one single bond, one electron pair is moving here. So it becomes O minus, isn't it? O minus, then O minus, then here what happens? This electron pair or negative, this electron pair will be moving towards this carbon atom. So here it becomes a double bond, isn't it? Double bond, then again one H is already there. Double bond, then again single bond C. Then here also the same process, that is the electron pair will be moving towards oxygen atom. Hydrogen will be removed as a proton. So this electron pair will be moving towards this carbon atom. So here also a double bond between 3 and 4, a double bond will be formed. So this is the third carbon, this is the fourth carbon, first carbon, second carbon. Okay. Then again single bond. O minus, isn't it? The electron pair will be moving towards this oxygen atom. Then again what happens? This H plus will be abstracted by this O minus, isn't it? So that it becomes OH. So we can remove this negative charge. Here also it becomes OH. Okay. Hydrogen will be here from this position. The hydrogen will be moving towards this O minus so that it becomes OH. Okay. So this is the enol form. There is no negative charge here. This is OH. So this is the enol form of this dicarbonyl compound. Then again for the synthesis of these three compounds, we are using this enol form. So this is the enol, that is a double bond is there, one OH is there. So this is in the enol form. So here we have to we have got the method of preparation. So in the enol form, if we are adding P2S5, that is phosphorus pentasulfide at 100 degrees Celsius. What will be the element which is introduced into the 5-membered ring? It will be this sulfur atom. Okay, so it will be a derivative of the sulfur atom. So the compound formed will be, I will be drawing the skeleton, eliminating this carbon. That means I will be drawing the skeleton only. So again, see here, double bond, then the two carbon atoms, these two carbon atoms, hydrogens are understood. Then again at this position, for first and fourth position, sorry, here one R dash is there. So at the first and fourth position, alkyl groups are there. So here at the first position R, then at the fourth position R dash. Okay, so this is the first compound. So what about the numbering 1, 2, 3, 4, 5? Okay, so this compound is 2,5-dialkyl substituted thiophene. So this compound is thiophene, isn't it? 5-membered ring with the sulfur atom, it is thiophene. So at the 2 and 5th position, second and the 5th position, there are two alkyl groups. So we can name it as 2,5-dialkyl substituted 2,5-dialkyl substituted thiophene. Okay. Then the next method of preparation, that is on treating with phosphorus pentoxide P2O5 at 160 degrees Celsius. See, phosphorus pentoxide, it is a dehydrating agent. So here one molecule of water will be eliminated. That means from this two OH groups, one molecule of water will be eliminated. That is H2O will be eliminated. So the remaining one will be the oxygen atom. Okay, this H2O will be eliminated. So here again we will be having a 5-membered ring, 2 double bonds. At the second and the fifth positions there will be an alkyl group. R and R dash are there here at this position. That is at the first position there will be oxygen atom. Okay. So again this is a 2,5-dialkyl substituted. The compound is, the hetero atom is oxygen, so it is furan. Dialkyl substituted furan. Okay. Then the next synthesis, the third one we have to prepare, that is pyrrole, isn't it? So here we are using ammonium carbonate, NH4 twice CO3, or we can use ammonia. Here 2 molecules of water will be eliminated, and again at the fifth, here what happens, 2 molecules of H2O will be eliminated, and here we will be having 1 NH. Okay. So the product will be pyrrole, NH. Again dialkyl substituted R, R dash. Okay, so this is again 2,5-dialkyl substituted pyrrole. 2,5-dialkyl substituted pyrrole. Okay, so this is the general method of preparation of these 3 compounds, thiophene, furan and pyrrole. Okay. So this is very important. Usually it will be asked in section C part, that is for a 4-mark question it is asked. So it is very important, 4-mark question. For 4 marks this question will be asked. Okay. Then we can move on to the next topic, that is regarding the general characteristics of these compounds, that is general characteristics. General characteristics. See here, normally these 3 compounds, that is pyrrole, thiophene and furan. These 3 are colorless liquids. And also the boiling points of furan. Boiling point of furan, it is 32 degrees Celsius. Thiophene, it is 84 degree, and pyrrole it is 131 degrees Celsius. Okay, so these are the boiling points of these 3 compounds. Then again in the case of this pyrrole has got a high boiling point, isn't it? Pyrrole has got a boiling point of 131 degrees Celsius for pyrrole. What can be the reason? See here, pyrrole, the structure it is like this. Sorry, I'll be drawing it like this. NH. So this is the structure of pyrrole, isn't it? Then this is another pyrrole ring, NH. Can you tell me here what happens? See here, sorry, NH. Okay, see here, there is a chance for a intermolecular hydrogen bonding, isn't it? See here, this hydrogen, it is bonded to this nitrogen atom. So here one hydrogen bond is there. So there is a chance for intermolecular hydrogen bonding. So as a result of this intermolecular hydrogen bonding, what happens? This boiling point of pyrrole is somewhat higher than that of thiophene. Okay, pyrrole has got the highest boiling point of 131 degrees Celsius due to intermolecular hydrogen bonding. That point is also very important. Why the boiling point of pyrrole is high when compared with that of thiophene? Due to this intermolecular hydrogen bonding. Then the next topic, that is the aromatic character of these compounds. Aromatic character of this 5-membered heterocyclic compounds. So here these heterocyclic compounds also exhibit aromatic character. That is the first point. Heterocyclic compounds will be exhibiting aromatic character, and also they will be behaving just like benzene, and also they will be resonance stabilized. Resonance stabilized, that means they will be having different resonating structures. Just like we are drawing the resonating structures of benzene, here also for this 5-membered heterocyclic compounds, we can draw this different resonating structures. So we can say that they are also resonance stabilized. And also the resonance energies of this these three, that is thiophene, pyrrole and furan. The order will be like this. The resonance energies of thiophene, it is greater than pyrrole, greater than furan. The resonance energies of thiophene is greater than pyrrole, it is greater than furan. So that means the furan it is having the lowest resonance energy. Furan is having the lowest resonance energy. And also we can draw the resonating structures of this particular compound. So here I am representing the heteroatom with X. Okay, double bond, 2 double bonds are there, and also 1 electron pair is there. So here X can be any heteroatom. It can be oxygen, sulfur or nitrogen. Okay, X can be oxygen, sulfur or nitrogen or NH. Okay. So the first resonating structure we can draw. So if it is resonance stabilized, we have to draw the resonating structures also. It is very important. This aromatic character of this heterocyclics are very important. So this is the first structure. Then you have to draw the electron shift of this particular compound. So this electron pair will be moving to this double bond. What happens to this double bond? It will be moving to this position. Okay. So what about the next structure? It will be like this. Then X, 1 bond will be remaining as such. This electron pair is shifted to this position. Then this double bond, it is shifted to this position, so that there will be a negative charge at that position. Okay. What about the next structure? It will be like this. This electron pair will be shifting here, and this double bond will be shifting towards this position. Okay. Again X. Already 1 double bond is there. So this electron pair shifted here. So a double bond will be there. This double bond, it will be shifted to this position. So a negative charge is there. Okay. Then here at the start here, 1 electron pair is shifted here, isn't it? So this X will be having a positive charge. I had forgotten to put the positive charge. Then again, in the next step, what happens? This electron pair will be moving to this position. Okay. Then what happens to this double bond? This double bond will be moving to this position. So the next structure will be like this. X plus. Then here a double bond. Already a double bond is there. Then this double bond will be shifting towards this position. That becomes the negative charge. Okay. Then the last structure. What happens in the last structure? See here. This electron pair will be shifting here, and this double bond will be shifting to this position. So this is the last structure. So X, again double bond, then again here it is a double bond, here 1 negative charge. Okay, so this is the last structure. So these are the 5 resonating structures. So here you have to study this electron shift. It is very easy also. You have to draw the electron shift of all these double bonds as well as this electron pair. So here how many double bonds are there? 2 double bonds and 1 lone pair of electrons are there, isn't it? For this delocalization. So here we have got 5 different resonating structures, and thereby we can say that the particular compounds, these 3 compounds are resonance stabilized. Okay. And also here at these positions there will be a carbon atom, isn't it? So we can say that all the ring atoms present in this particular compound, it will be in the sp2 hybrid state. That is the another important point to be noted down. That is, all the ring atoms will be in the sp2 hybrid state, and also the ring is a planar one. The ring is a planar one. That means it will be in the same plane. And also here, how many electron pairs are involved in delocalization? How many electron pairs? See here, 2 electrons, then plus 2, 4, plus 2, isn't it? So in total there will be how many electron pairs? 6 electrons are involved, isn't it? 6 electrons are involved in delocalization. 6 electrons are involved in delocalization, and among these 6 electrons, how will you categorize? 2 pi electron pairs, isn't it? These are the 2 pi electron pairs and 1 lone pair of electron. Among these 6 means 2 pi electron pairs, 2 pi electron pairs and 1 lone pair of electron. And 1 lone pair of electrons are involved in delocalization. Okay, so this is how this compound exhibits aromatic character. So these are some of the reasons for this compound to show aromatic character. So the first point to be noted down, it is that this is resonance stabilized. Then you have to draw the 5 resonating structures. Then you have to show the resonance energies. Thiophene has got the highest resonance energy and furan has got the lowest resonance energy. Then the ring atom will be in the sp2 hybrid state. The compound is planar and also it has got 6 electrons involved in delocalization, that is 2 pi electrons and 1 lone pair of electron. Okay, so these are some of the this is also an important point, that is aromatic character. It will also be asked in the C part sometimes, section C. It will be asked in the C part. Okay. Then the next is the reactivity of these compounds. Reactivity of this thiophene, furan and pyrrole. So here, while comparing this, the reactivity of these compounds with benzene, benzene has got the least reactivity. That is benzene less than thiophene, less than furan, less than pyrrole. So which one will be the most reactive? Pyrrole will be the most reactive and benzene will be the least reactive. Okay, pyrrole will be the most reactive and benzene will be the least reactive. Then see here, this furan is also less reactive than pyrrole, because see this in the case of pyrrole, in the case of furan and pyrrole, we can see that here this oxygen, in the case of furan, the structure it is like this, one oxygen atom, isn't it? But in the case of pyrrole, the structure it is NH. So this nitrogen will be accepting the positive charge more readily than this oxygen atom. Okay, this nitrogen will be accepting a positive charge more readily than oxygen atom. So that means this pyrrole, it is more reactive. Then similarly in the case of thiophene and furan also, while comparing the case of thiophene and furan also, in the case of thiophene, it has got sulfur, isn't it? The heteroatom, it is sulfur. So this sulfur atom, it has got a mesomeric effect, plus M effect, and due to this this plus M effect of sulfur, it is smaller than that of oxygen atom. Hence thiophene, it is less reactive than furan. So these are the two reasons. In the case of while comparing furan and pyrrole, nitrogen atom will be easily accepting a positive charge than this oxygen atom. And while comparing the reactivity of thiophene and furan, sulfur has got a plus M effect smaller than that of this furan. Okay, so these are the two reasons of the lower reactivity of thiophene and the lower reactivity of furan. Okay, so the order it will be like this: benzene will be the least reactive, then thiophene, then furan, then pyrrole. So the most reactive one, it is pyrrole. Okay, then coming to the electrophilic substitution reactions or the chemical properties of these compounds. Electrophilic substitution reactions. In electrophilic substitution reactions, what about the attacking species? The attacking species will be a positively charged electrophile, isn't it? That is E plus. E plus will be attacking this heterocyclic atom, isn't it? And also we had seen the alpha as well as the beta positions, isn't it? Alpha position means it is the 2, 5 position, and beta position means it is the 3 and 4 third and fourth positions, isn't it? So at what position this E plus will be attacking? That is very important. That is where electrophilic substitution, at what positions electrophilic substitution will take place. Whether it is at the alpha position or it is at the beta position. That is another point to be noted down. And also in these cases, the electrophilic substitutions will be generally occurring at the alpha position. Okay, this electrophilic substitution or the E plus attack will be normally taking place at the alpha positions, that is at the second and the fifth position. That is that point also to be noted down. Okay, then we can go through the next compound, the first compound, that is thiophene. So here we have to discuss the physical as well as the chemical properties, some methods of preparation also in this thiophene, in the case of thiophene, that is C4H4S, and the structure it is like this. Okay, so this thiophene, it was discovered by Victor Mayer in the year 1882. Victor Mayer, and also some of the methods of preparation of thiophene. The first method of preparation, first method of preparation, that is by heating sodium succinate. By heating sodium succinate. By heating sodium succinate. Succinic acid means the formula it is like this, CH2, COOH, isn't it? So this is the structure of succinic acid. So sodium succinate means this OH will be replaced by ONA. That is, it becomes COONA. Here also this OH is replaced by ONA. That is COONA. So the compound will be like this. This is succinic acid. So the sodium salt of succinic acid, that is sodium succinate. That is CH2, single bond CH2, then CO, again CO, then again what about the next position, that is ONA. ONA, here also ONA. So plus by heating sodium succinate with P4S7 or P2S3. A sulfur containing compound P2S3. So this is P4S7 is tetraphosphorus heptasulfide. Tetraphosphorus heptasulfide. Tetraphosphorus heptasulfide. I am writing in short here. You have to do it completely. Tetraphosphorus heptasulfide. So by heating with this compound, we will be having thiophene. A simple reaction. So this is thiophene. Plus 4NaPO2S, that is the byproduct that you can ignore. Okay, so here the major product is thiophene. So that is the first method of preparation of thiophene. Then the next one, that is the industrial method of preparation, second one. Industrial method of preparation means in a large scale or in a commercial basis. So the starting compound is normal butane. Normal butane. It is treated with sulfur at a very high temperature of about 650 degrees Celsius. You will be having thiophene. So normal butane. Normal butane means it will be having 4 carbon atoms. Okay. So I will be writing it like this: CH2, CH2, CH3, CH3. So this is normal butane, isn't it? I am putting it in just like a ring form, isn't it? But it is a straight chain compound, not a ring closure. CH3, CH2, CH2, CH3 plus 4S at 650 degrees Celsius, we will be having thiophene. Plus 3H2S. Sorry for the noises here. So this is the industrial method of preparation of thiophene. That is a large scale method of preparation. Okay, a simple reaction. Then the third reaction, that is bypassing a mixture of acetylene and H2S. Acetylene when passed over H2S over heated alumina, Al2O3, over heated alumina. This is also a commercial method of preparation. commercial method of preparation of thiophene, that is when acetylene it is passed over H2S over heated alumina. Acetylene means the formula it is CH triple bond CH acetylene, 3 molecules of acetylene plus hydrogen sulfide in the presence of alumina Al2O3 at 400 degrees Celsius. Al2O3 400 degrees Celsius, the product will be thiophene. The product will be thiophene plus H2S. Okay, so this is the third method of preparation. Then coming to the fourth method of preparation, that is normally this thiophene it is present in this commercial benzene. Commercial benzene, that is benzene of coal tar origin. So we have to isolate this from this benzene. Okay, so this isolation from benzene, and this benzene it is from coal tar origin, so we have to isolate from this benzene. Isolation from benzene of coal tar origin. So here first of all we have to treat this benzene, that is we are separating it from benzene, isn't it? So we have to treat this benzene with cold concentrated sulfuric acid. We have to treat it with cold concentrated sulfuric acid. So what happens is that this thiophene will be easily sulfonated than comparing with that of benzene. That is, while comparing this benzene and thiophene, which one is most reactive? Thiophene is most reactive, isn't it? So when benzene, that is benzene, it will be having thiophene also. It is a mixture of benzene and thiophene, and we have to isolate from that mixture. We have to isolate this thiophene. So when this this mixture of benzene and thiophene, when this mixture of benzene and thiophene it is treated with cold concentrated sulfuric acid, what happens is that since thiophene is more reactive, thiophene will be easily sulfonated. Okay, so what happens is that thiophene will be more readily sulfonated than benzene. That is, at the second position it will be having SO3H. Okay, so thiophene will be more readily sulfonated than benzene. And again this thiophene sulfonic acid, so we will be obtaining this thiophene sulfonic acid, and then it is treated with water, and this one is water soluble, so we can separate it from benzene. Benzene is not water soluble, isn't it? So here thiophene sulfonic acid, when it is treated with water, it is water soluble, so we can separate it from benzene. Then on steam distillation, so this compound is water soluble, this compound is water soluble, and again what happens is that, sorry for the noises going on here, please excuse me. So here this thiophene sulfonic acid is water soluble, and then it is steam distilled. This compound is steam distilled. On steam distillation we will be obtaining thiophene. On steam distillation we will be obtaining thiophene. Okay, so this is how this thiophene is isolated from benzene. So a mixture of benzene and thiophene, it is treated with cold concentrated sulfuric acid. So thiophene is more reactive than benzene. So thiophene will be converted to thiophene sulfonic acid. Then, and also when it is extracted with water, it is water soluble. So we can separate it from benzene. Then again that particular compound, it is steam distilled, and when steam distilled we will be obtaining thiophene. Okay, so this is the preparation, last method of preparation of this thiophene. Then next, coming to the properties, it is a colorless liquid. We had already seen colorless liquid, and also physical properties of thiophene. Physical properties of thiophene. It's a colorless liquid. Colorless liquid, and also the boiling point of thiophene, it is 84 degrees Celsius. Then thiophene is more reactive than benzene also. Then it will be undergoing electrophilic substitution reactions. Okay, it will be undergoing electrophilic substitution reactions at the what position substitution will be taking place? At the second and the fifth positions, the substitution will be taking place. Then the next is the electrophilic substitution reactions. Electrophilic substitution reactions of thiophene. Electrophilic substitution reactions of thiophene. Thiophene. First reaction, that is chlorination. Chlorination. So chlorine will be taking the second position, isn't it? It is an electrophile. So here, see, a chlorine will be acting as an electrophile. So all these, that is halogenation, sulfonation, nitration, etc. will be taking place at position 2. So at the second position, we will be having one chlorine atom, and the compound is called as 2-chlorothiophene. 2-chlorothiophene. Then the next one, that is bromination. Bromination. These are all simple reactions. You just keep in mind the positions of the electrophile. Okay, bromination. So here, this bromination, it is much more here bromination will be taking place at the second as well as the fifth position. Okay, so the compound, it is 2,5-dibromothiophene. 2,5-dibromothiophene at the second and the fifth position. Similarly, all the reactions will be going on. Then the next one is iodination. Iodination in iodine in presence of silver oxide, AgO. So here iodine will be substituted at the second position only. That is 2-iodothiophene. The remaining you have to write, okay, 2-iodothiophene. Then the next reaction, that is nitration. Nitration means which group will be introduced? NO2 group will be introduced, and also since it is an electrophilic substitution reaction, NO2 will be introduced at the second position. So here for nitration, we are using a mixture of acetyl nitrate. So we are using acetyl nitrate. Acetyl nitrate, the formula is CH3COONO2. Acetyl nitrate. It is a mixture of acetic acid as well as nitric acid. Okay, mixture of acetic acid CH3COH and nitric acid HNO3. So one molecule of water will be eliminated, and this compound, it is acetyl nitrate. Acetyl nitrate. Okay, acetyl nitrate and acetic anhydride, both the reagents are used here. Here also NO2 group will be introduced at the second position. NO2 will be introduced at the second position. So again, it is 2-nitrothiophene. So the remaining you have to write, okay, 2-nitrothiophene. Then again nitration, somewhat under vigorous conditions, that is nitration using concentrated nitric acid. Nitration using concentrated nitric acid. So here, sorry, S, it is S here. Then here we will be having 2,5-dinitrothiophene. 2,5-dinitrothiophene. Nitration using concentrated nitric acid. Then the next one, that is sulfonation. Sulfonation. For sulfonation, normally we will be using sulfuric acid, and room temperature is maintained. Room temperature is maintained, so we will be having S. Then at the second position, we will be having SO3H, that is sulfonic acid group, SO3H group. So this compound is 2-thiophene sulfonic acid. 2-thiophene sulfonic acid. Okay. Then the next reaction, that is Friedel-Crafts reaction. Friedel-Crafts reaction. Friedel-Crafts reaction, normally we will be using acid chloride, isn't it? That is the reagent, acid chloride, CH3COCl in presence of SnCl4, stannous chloride. So here, which group is introduced? CH3CO group will be introduced at the second position. That is, this part will be introduced. So at the second position, yes, second position, COCH3. Okay, at the second position, the CH3CO group will be introduced. So the compound is 2-acetyl. So this is at the second position, 2-acetyl thiophene. 2-acetyl thiophene. Okay. Then the next one, that is chloromethylation. Chloromethylation. For this chloromethylation means we will be introducing one chlorine atom as well as methylene group. Okay. So for that we will be using formaldehyde, HCHO and HCl. Formaldehyde and HCl. So the product formed will be like this. At the second position, CH2Cl group will be introduced. So the compound is 2-chloromethyl thiophene. 2-chloromethyl thiophene. So here the reagent used is formaldehyde and HCl. So 2-chloromethyl thiophene. Then one more reaction, that is mercuration. Mercuration reaction. Here we are using acetyl mercury, CH3COO twice Hg in presence of water. Hg in presence of water. So we will be having acetoxy mercury thiophene, that is S, then Hg, COO, CH3. So this group will be introduced. CH3COHG will be introduced at the second position. Okay. CH3COOHG will be introduced, and one byproduct will be acetic acid. That is, from this position one hydrogen will be going with CH3COO. Okay. So this compound is 2-acetoxy mercury thiophene. 2-acetoxy mercury thiophene. Okay. Then you have got two more reactions that will be discussed in our next session. Okay. So please write the lecture notes also. Don't forget, for organic you have to you have to write the lecture notes. Otherwise you will not be get familiar with the reactions. Otherwise you will be forgetting the reactions as well. So organic chemistry you should be studying by writing itself. No other way for writing. Just you are doing this mathematics problems. Okay. So you have to write the reactions. So here these are all simple reactions. You have to study the reagents, and the corresponding elements or the corresponding groups will be introduced at the second position, or it can be at the fifth position. So for halogenation, the halogens will be introduced at the second position. For nitration, NO2 group will be introduced. Then for sulfonation, SO3H group will be introduced. Then Friedel-Crafts reaction means acyl group will be introduced, that is CH3CO group will be there. Then for chloromethylation, one CH2Cl will be introduced. Then mercuration, then say CH3COOHG will be introduced. Okay, so you have to study the at what position this electrophile will be attacking that particular compound. The two more reactions are remaining there. We can take I will be taking that in our next session. Okay, thank you and have a nice day.